Okay, so good morning. This is the third week in flight mechanics. The first 2 weeks we spent quite some time to review system dynamics, really. So last week we just started really on flight mechanics. And the first thing I did was I started explaining coordinate systems and reference frames that we commonly use in flight mechanics. So to review very quickly what I did last week, we started defining the reference frame. We said a reference frame is a rigid body or a set of rigidly connected points that can be used to define velocities, accelerations. Basically, that defines motion. So that's kind of an important thing, because we define motion based on reference frame. The motion of something, or the observation of the motion of an object, is observed differently from different reference frames. We said someone looking at an airplane from Earth or from space, or someone looking at the movement of a car from Earth or from space might observe different velocities and accelerations. So this was kind of important. So the concept of reference frame, I think we spent a lot of time on that in the past few weeks. The other important part that we talked about is the coordinate system. We said the coordinate system is a measure or a device usually attached to the reference frame. It's a measurement device, really. It has nothing to do with reference frames. We can attach it to a reference frame, but it is not the reference frame. So I can have a movement of an object with respect to a reference frame and then write it in any coordinate system I want, right? So that's the definition of the coordinate system. And then we moved on and we said last week, let's define reference frames and coordinate systems that are commonly used in flight mechanics. And I started with the first one. The first one was the body fixed coordinates, the body fixed frame, or what we call the body fixed coordinate system. So the body fixed reference frame is basically the airplane itself. So from an observer on the airplane, you are observing the world, the airplane, the stars, whatever. So that reference frame is not particularly useful. However, the body fixed coordinate system that we attach on that reference frame is of big importance. So we attach the coordinate system to the airplane and we call it the body fixed coordinate system. FB refers to the body fixed reference frame, and we define the body fixed coordinate system. So the way we define it is that XB is towards the nose of the airplane, YB is to the side, and ZB is downward, typically in the symmetry plane of the airplane. Symmetry axis. So when I say symmetry axis, I really mean this. You know, you have an airplane like that, and this would be the symmetry axis here. Okay? This is the symmetry axis. Okay? So ZB and XB would be in the symmetry axis and YB would be to the side. We also talked about the right-handed coordinate systems. So basically you take your four fingers, go from X to B, and Z must be pointing towards the Z direction. It is attached at the CG, and that is your body fixed reference frame. Okay? Do you have any questions from last week? So I think this is kind of where we stopped. Okay? Good. So the next coordinate system that I want to talk about is what we call the vehicle carried coordinate system. Vehicle carried reference frame or vehicle carried coordinate system. And in this class we shall call it with an FV, V standing for vehicle carried coordinate system. Now this coordinate system is quite similar to the body fixed coordinate system, except there is one subtle difference. This is my airplane, okay. xv, this is the x-axis that is attached to the vehicle carried coordinate system, will always point to the north, not towards the north of the airplane, will always point towards north, okay? And ZV, actually this ZV is the deciding factor, the deciding axis. ZV is pointing towards the local gravity vector. Points towards the local gravity vector. So the Earth acceleration is in this direction, so ZV must be along G. Okay? This is the most important one. ZV has to point towards the gravity vector. And then you can, of course, point XV and YV the way you want, but in this class we will be pointing XV towards north and YV towards east. Okay? So YV is pointing east, XV is towards north, ZV is towards the local gravity vector. We sometimes call it down, ZV is pointing downwards. So it's like a northeast down coordinate system. Okay, sometimes we call it northeast down coordinate system. But I would prefer in this class to call this the vehicle carried coordinate system, where ZV is pointing towards the local gravity vector, XV is pointing north, and YV is pointing east. Okay? Now, this is attached at the CG of the aircraft, and this is always the case. Which means if the airplane starts rotating, XV is still pointing towards north. So if you had an airplane that was looking like this, okay, and this is a CG and it's flying this way, XV would still be in this direction. Which way would be the Y coordinate system? Would it be into the plane or out of the plane? Use your right hand. Which way would it be? Into the plane or out of the plane? Into the plane, right? So what you do is you take your right hand, go from X to Y, and Z is pointing downward, right? So it is into the plane. So YV is still into the plane. Still looks like that. Okay? And note that they are parallel now. They are still in the same direction. XV is same, YV is same, ZV is same, you see? Think of an airplane going upwards. Going straight upwards, and this is a CG. Where would be the vehicle carried coordinate system? XV would still be pointing north. Okay. ZV would still be pointing towards the local gravity vector, and YV would be pointing inwards, such that it is a right-handed coordinate system. Okay. Where is the body fixed coordinate system for this? The body fixed coordinate system would be pointing towards the nose, right? It would look like that. The x-body coordinate system. The x-body coordinate system for this one would be pointing like that. This would be x-body, right? And z-body would be perpendicular to this. It would look like this. This would be z-body, the body fixed coordinate system. Remember, the body fixed coordinate system is attached to the airplane, moves with the airplane, and rotates with the airplane. The vehicle carried coordinate system is attached to the airplane, it moves with the airplane, but does not rotate with the airplane. Because XV is always pointing north, YV is always pointing east, and ZV is always pointing down. Okay. Now you might, this is of course true if the local gravity vector and north, you know, if they are pointing like that, they are 90 degrees to each other. If there's a discrepancy somewhere and the Earth is not a perfect sphere, then it might not be exactly 90 degrees, but for a coordinate system, it must be 90 degrees. So therefore, the assumption is that the Earth is a perfect sphere and things like that. Whatever we do, when we build this coordinate system, we first start with ZV, look at the local gravity vector, and try to point XV towards north. Of course, it's 90 degrees, and then you finish the right-handed coordinate system, and that's YV. Any questions of the coordinate systems, the body and the vehicle carried? Okay, you understand the difference. Now, the vehicle carried coordinate system can, of course, be also a reference frame. Basically, something that that moves with the airplane, but doesn't rotate. It could be viewed as a reference frame. Not a very useful one, but the coordinate system is indeed very useful. Okay? Any questions? Do you understand the difference between body fixed coordinate system and vehicle carried coordinate system? All right? Very important. Good. So, the third one, this was number 2, the second coordinate system. The third one is, we are looking for other reference frames. The third one is, of course, Earth, right? The Earth fixed coordinate system. Earth fixed reference frame. And we have Earth fixed coordinate system. So it's a coordinate system that is attached to the Earth. Okay? So if you take Earth, you know, take it like a perfect sphere. Let's see, this is Earth, and this is the North Pole, and this is the South Pole. Okay? Obviously, the Earth is a reference frame, and this is a reference frame that we use a lot in our daily lives because we live on Earth and everything is with respect to Earth, right? We stand on the Earth and make observations and make conclusions about motion, velocity, and acceleration. The Earth fixed reference frame is very often used also as the inertial frame, but that's, as we talked in the past weeks, it is only an approximation. But it works quite well, at least for most of the cases that we are using in aerospace, unless you're going really fast or something. Okay, so the coordinate system, the Earth fixed coordinate system is designed in such a way that you pick any point on Earth, any point, okay, you can attach your coordinate system anywhere you want on Earth. Preferably you attach it close to where you want to analyze the airplane. Close to the airplane, because it's too far away, it doesn't make much sense. It has to be close to the airplane where you want to do the analysis. And again, the z-axis is pointing towards the center of the Earth, which is towards the local gravity vector. But let's call it towards the center of the Earth. So ZE is pointing towards the center of the Earth. Again, the center of the Earth, because it's not a perfect sphere, there's a slight difference sometimes depending where you are. But in this class, we assume a perfect sphere, and that's a good enough approximation that Z is pointing towards the center of the Earth. Okay? And then the other two, you can point somewhere. You could point in any direction you want, but again, in this class, XE. This is XE. The X coordinate system will point towards the North Pole. And this is here ZE. And YE will be therefore pointing towards east. Okay? So you could attach it anywhere you want. You could attach the same coordinate system somewhere here. So ZE would be pointing towards the center, XE would be pointing towards the north, and YE would be pointing east. Okay? So that's the Earth fixed coordinate system. You can also see that if the Earth was flat, or if the airplane is exactly over that coordinate system, that the vehicle carried coordinate system and the Earth fixed coordinate system are parallel. I mean, the axes are parallel. So XV is pointing towards north, so is XE north. YE is pointing east, so is YV is pointing east, so is YE. So ZV is pointing towards the center, local gravity vector, so is this one. The only time when this is only true when they're on top of each other, or you assume a flat Earth, or you made a flat Earth approximation. Of course, when the airplane starts moving around the Earth, okay, then they are not parallel anymore. You see that, right? They are not parallel when they start, when the airplane is rotating around the Earth. So, any questions? Yes?
So, the second coordinate system you wrote, is it okay for a right-hand rule?
Well, it should be. If it isn't, then... Oh yeah, this is... Thank you very much. I mean, I say east, but this is obviously pointing... Is it pointing east? Yeah, okay, so that is correct. So that should be... Yeah, they're all correct. It's not obvious from here, yeah? X to Y pointing towards the center, all right? X to Y pointing towards center. It must be, it's not very apparent from this picture, but it must be pointing towards the center. So XY pointing down. So it doesn't matter which way I look, okay? If this is north, this is east, XY pointing downwards. It's not a very good picture, and that's a pretty picture at least, okay? Is that okay? Any other questions? All right. So there is one more coordinate system that is related to the Earth, and we are not using it too much, but when the Earth rotation is of importance, we use that too sometimes. It is the Earth centered coordinate system. As I said, we are not going to use this in class, but it's a very obvious one. So things like the GPS satellites, for instance, use that coordinate system, right? So you do this, you do that, and you have the center of the Earth. And what you do is you're pointing XV towards the North Pole, XE centered. Okay? And then you attach... just one second. I don't want to make a mistake there. Just we don't make mistake. Yeah, I thought so. The one that's pointing towards north is Z. It's wrong. ZEC. Okay, that's north. That's pointing towards north. And XEC and YEC, they are in the plane of the equator. Plane of equator. Okay, so you can attach it anywhere you want now, so that as long as it is a right-handed coordinate system. So XEC, let's do it like this, YEC. So XEC and YEC, the X and Y coordinate system are along the equator, and Z has to point upwards. So this is again a bad picture. XY, let's put it like this. Let's put it YEC like that. This is a horrible picture actually, so let's do it like that. XEC, YEC, and Z is pointing upwards towards the North Pole. Okay, so these are in the plane of the equator. This is the equator. And this is pointing north. So this is a typical Earth-centered coordinate system. And satellites and things like that are obviously using the Earth-centered coordinate system. But we are not going to use this at all in this class. We are really interested in the Earth-fixed coordinate system and the vehicle-carried coordinate system. Does that make sense? Is that okay? Any questions? All right. I have 2 more coordinate systems, so you have to ask questions when you get confused. Okay, number 4. That's the easier one. Okay, no. Let's call this I just wanted to make sure I got this name right. It's the air trajectory reference frame, and the coordinate system that is attached to that is called the wind fixed coordinate system. Now, let's say you have an airplane. Again, let's plot it like that. And let's say the local velocity vector that this airplane will see is this one. This is V infinity that you have learned in flight mechanics. Not in flight mechanics, in aerodynamics, right? V infinity. So you have this V infinity. This is the local velocity vector, the air velocity vector. So using that air velocity vector, we are attaching a coordinate system to the airplane. This is how we do it. We again attach it at the CG, the center of gravity of the airplane. So XW, I mean the wind axis coordinate system, is pointing towards V infinity. Okay, so XW points towards the local air velocity vector. Okay, towards the local air velocity vector. ZW is 90 degrees to XW, but it is such that it is in the symmetry plane of aircraft. ZW is in the symmetry plane of the aircraft. So the symmetry plane, as I said at the beginning, if this is your airplane, this is your symmetry plane. Okay? And ZW must be in this plane. Understand? So if you have a symmetry plane, it must be in that plane. So it's here. And that is ZW. And YW is such that it forms a right-handed coordinate system. So the right-handed coordinate system, it must be in this direction in this picture. Okay? It forms a right-handed coordinate system, so it must be like that. Now, as V infinity is changing, XW, the direction of XW will change with it, right? For instance, if you had an airplane where V infinity is coming from the top, this is a strange picture, of course, it's probably an airplane in stall. XW would be like that. Okay, xw would be like that. It would be towards v infinity. zw would be in the symmetry axis, but 90 degrees to xw. And yw would be such that it is a right-handed coordinate system. It would be like that, into the plane, basically. xw must be towards v infinity. Okay? Understand? You don't believe? Do you understand it or not?
Does it obey the right hand rule?
Yes, it's supposed to.
It doesn't.
So yw is into the plane. Yw is into the plane. I just can't plot it into the plane. Do you understand this at all? V infinity is pointing towards xw. Zw is 90 degrees. So which way is Zw is 90 degrees to xw in the symmetry plane of the airplane. So which way should be yw? Into the plane, right? Isn't it? Do you understand that? Look at this one. Look at this one. X is pointing this way, y is into the plane, and z is downwards. X to y, and this is z. X is pointing towards v infinity. Yv is into the plane. So I pointed, sideways. I'm trying to do a 3D picture, but it's not very good. It is into the picture. So xw, y, and this is z. So the way you do this, you form this body axis, this wind axis coordinate system is, you start with xw. You make sure it is parallel to v infinity. And then you take your right, and then you plot zw, which is in the symmetry plane of the airplane. Then you take your right hand and form yw such that it's a right-handed coordinate system. So yw is into the plane, xw, zw, that's your coordinate system. You have an axis, a three-dimensional coordinate system that is attached to the CG and moves with the airplane, but xw always points towards v infinity. Understood? Yes? Reverse direction? Well, it depends how you want to define it, but as long as vw is coming from that direction, we always point zw over here, in this class at least. So if v infinity comes from here. The question comes, if v infinity comes from there, then it seems like zw is also pointing upwards. Typically, you could do it any way you want, of course. It could be up or down. But we kind of prefer this all the time. But if you stick with one way, if you have this, and vw moves this way, so you would slowly move it like that. Imagine v infinity moves this way, like that. So x would be moving with it. So z would be start pointing upwards, right? So I would stick with one convention. For beginners or for in this class, I would just start always pointing zw downwards. But you could certainly point it upwards, then y would be pointing this way. Okay? Yes?
What if we have gust?
Good question. What if we have wind? Okay? Or a gust? Or basically movement in the atmosphere. That movement in the atmosphere would be included in v infinity. Okay? V infinity includes wind. That means it is the local air velocity. So the local air velocity could be because of many things. If the atmosphere is still, it is because I am moving. Or it could be because I am moving, but there's also air blowing from the front. So that is v infinity, right? In aerodynamics, it doesn't matter if I go towards the air or if I stay and the air moves towards me. Both will create lift and drag, isn't it? Isn't it like that? So this is how a wind tunnel works, right? If the atmosphere is still, I can go in the air, and standing from the air, I can look at the air and say the air is coming towards me. That's the reference frame of the airplane, right? Or you can just sit in air, like in a wind tunnel, and someone can blow air at you, you would still be sitting on that airplane and say, air is blowing towards me. Doesn't matter how the relative velocity of the air with the airplane is, if I have air coming towards me, I will create lift and drag. So, therefore, this V infinity is the relative movement of the air with respect to the airplane. It could be because I am moving, as a result, relatively, the air is moving towards me, or I am standing and someone is blowing air at me, or it is a combination of both, which means I am flying, therefore the air is moving towards me, plus there is a wind. You add them together, that's V infinity. This is the definition of V infinity in aerodynamics. Okay? Now, the air doesn't always have to blow from the front, it could be from the back. So then you subtract those two velocities. But it could also be from the side. Right? Then what happens, what is V infinity when air blows from the side? Which means I go this way and there's air blowing from the side. V infinity will be the vector combination, will be the vector addition of those both. And V infinity will actually be from the side. Right? Let me plot this for you. For instance, let's say I have an airplane that is flying with a velocity of certain velocity, I don't know, V. And we are looking now from the top. We are looking at this picture from the top. Okay? And let's say this is the velocity of the airplane. Whenever I tell you the velocity, what information do I need to tell you? This is the velocity of the airplane with respect to a reference frame. What reference frame? Let's call it the Earth. Or like that. Okay? It is the velocity of the airplane with respect to Earth. So someone looking from the bottom at the airplane will see this velocity of the airplane. So it's moving this way. Which also means if the atmosphere is still, if the atmosphere around the airplane is still, V infinity would be like that, isn't it? Isn't it? Okay. Now imagine that the same airplane is moving with this velocity, however, also has a side velocity. Okay? Someone is blowing, that's some wind blowing from the side. Which means if there was no wind, this would have been V infinity. But now you have this wind which is going this way. As a result, V infinity is actually the vector combination of these two, and this is V infinity. So this is V infinity now. Understand? The air, the net air that is moving towards the airplane is V infinity. If the atmosphere is still, nothing is moving, the airplane is moving like that, which means the same and the opposite direction would be V infinity because the atmosphere is still. But if the atmosphere is not still, which means there's a wind blowing from the side, I will be moving with this velocity. The same and opposite would come from here because of the movement. And then because of the wind, you would add these two, and this would be the direction, this would be the direction of the air particles towards the airplane. So all air particles, they actually move like that to the airplane. Why like that? Because they are moving towards this way, and also this way, relatively of course, because I'm moving in this direction. Understood? Although the airplane is moving in this direction, the airplane is obvious. This is the velocity with respect to air, with respect to Earth, right? So obviously the airplane is moving forward. But because of the wind, V infinity is the forward velocity of the air plus the side wind, so this is V infinity. Okay? Now, if this is V infinity, which way does XW point? Let me do that. If this is V infinity, which way will XW point? It will point towards V infinity, obviously, right? ZW into the plane, in the symmetry axis, and YW would be such that it has a right-handed coordinate system, so VW would look like that. But XW would always point towards V infinity. Understood? Let me tell you another situation. Let's say there is no wind. No wind. And the airplane is indeed flying in this direction. So this is the velocity with respect to Earth. This is the velocity vector of the airplane with respect to Earth. So it is flying sideways and there's no wind, so the atmosphere is still. Which way is V infinity? It's the same direction, it's like that. Because there's no wind, if I'm flying sideways, so V infinity must be like that. So the air particles will appear to me as if they are moving towards the airplane. In fact, I'm moving towards the air particles, but that's the reference frame. But in fact, yeah, the airplane is moving towards the air particles, but from aerodynamics point of view, from the reference frame of the airplane, the particles are moving towards the airplane. So what is the direction? The direction is actually like that, because I'm moving towards them. In this case, I'm moving forward, but there's a side wind, it's still the same V infinity. So aerodynamically, it's the same picture. Except in one, I'm moving sideways. In this one, I'm moving forward, but there's a side wind. Aerodynamically, it's the same. And in both cases, XW would point in the same direction. You understand the difference? So let me show you with my little airplane here. I have too many cables now. So if this is your airplane, okay? So you're flying straight forward. If this is my velocity vector towards you, V infinity would be like that, right? Flying like that, this would be V infinity, flying like this. However, let's say you have an airplane that is flying like that. So the velocity vector is like this, which means V infinity is like that, right? Or I'm flying like this and there's a side wind from here. If there was no side wind, this would have been V infinity, but because of the side wind, now V infinity is like this. Understood? This is what we call a side slip. We will talk about this a lot more later. This angle is the side slip. But you understand that point? Okay. So this is the wind fixed coordinate system. Wind fixed coordinate system. So let's give a 5 minutes break. Let's make it 5 minutes because I started late. And please come back in 5 minutes.